Hi, I'm Richard with Savage Automation. Today I wanted to talk a little bit about tapered shutoffs and injection molds. This is kind of brought on by we're working on an end of arm for a mold that's got a stripper plate. And in a stripper plate mold, you have a core and you have a stripper component that pulls the plastic part or pushes the plastic part off of the core. And in that case, you use a tapered shutoff. So I created an example here of a core and a stripper sleeve for this. And if we go ahead and we take a section view of this, we can see how this works. So this core pin is going to stick out into the mold cavity. And our blue section here, this is where the plastic is going to get molded over top of. So this is the negative shape of the part. It's going to create the hole in the part. And then when we're done molding it, this stripper sleeve is going to move forward here, and it's going to catch the lip of that part and push it off of our core so that it can drop down into a bin, or if you're smart, into the arms of a waiting end of arm tool so that it can be picked out and taken and placed in a part separator or onto your conveyor. So why do we use a tapered shutoff here? Well, it's actually pretty simple. The reason being is a tapered shutoff, as soon as these parts move away from each other, so when the stripper plate or the stripper sleeve moves forward, there's very little friction. After that first little bit of movement, now the surfaces don't have to touch at all, right? Now, if you imagine a straight shutoff, if we just had it straight, that would be a lot of friction. The whole travel of the stripper, you would have friction against the stripper sleeve and the core pin. And imagine you do that a million times, you're going to wear out and start to cause problems. So the taper is going to prevent some of those problems. Now, we're going to mold this part out of polypropylene. So it's important to think about what material we're molding for a lot of reasons, but in this case of our shutoff, we've got to know at what point polypropylene will flash. Now this varies depending on which resin you're using and your process parameters of your molding machine, but a good rule of thumb for polypropylene is 1.5 thousandths of an inch. That's where we start to flash at. So we've got to keep the space in between this component and this component to less than that 1.5 thousandths of an inch. We've also got to take into account where the air will go. So a mold cavity, when the mold closes and it's getting ready to have the plastic injected into it, is full of air. And that air, when the plastic is injected in, it has to go somewhere. The plastic is injected in at high speed, and if the air doesn't have a proper place to go, it can get over-compressed very quickly and actually cause burning on the part. Or if it just doesn't move quite fast enough, it can make the part hard to completely fill with plastic, resulting in what's called a short shot. Right? So we have to have room for air to escape, but not enough room for any plastic to escape. When plastic gets in between these two parts, we call it flash. It's plastic where it wasn't supposed to go. It's not part of the product you're trying to manufacture. So, with those things in mind, let's take a quick look at this. On this core pin, our red area here, that's our shutoff area. That's the part that's going to meet up with the stripper sleeve and make it so plastic can't get in there. This yellow portion is what's called a vent dump. So the air we talked about that needs to get squeezed out of the mold, the vent dump is to give that air a good place to go. That air is going to contain plastic gases and residues and different off-gassing from the plasticizers that are part of the plastic. That's all going to end up going out with the air from the mold. And so the vent dump really gives a place for that stuff to build up. And it does build up. When you pull a mold to do a preventative maintenance cleaning on it, you'll find in these vent dumps, especially with certain resins, that they're really clogged up full of stuff. That's one of the important reasons to pull that mold and clean it regularly, is to get the vent dumps clean and allow the mold to continue to work properly. Now these are vent dumps. They're not the actual vent. The actual vent is going to be right here on this surface. We'll talk about that more when we go over and talk about tolerancing, but this is actually going to be relieved a little bit smaller than the rest of this shutoff surface to allow that air to escape through there and out into the vent dump. We go back to our section view here. You can see our vent dump leads out to an area of clearance here. And then in the mold plates, you'll usually have more vent dumps cut in so that that air can go all the way out to, we call it going out to atmosphere. It's got to have a good path to get out to the open air. So that's why we don't have a tight fit in between these two surfaces. We've already got our shutoff, and this is going to be left clear for air to get out. Okay, now if we just look at our sleeve, same thing, this red area is our shutoff surface. That's going to be really critical. You can see, actually, when you're handling mold components like this is an area to be really careful of. It comes up to a sharp corner on purpose. And if this gets damaged, it's going to result in flash. It's going to result in your shutoff not functioning properly. So careful handling of this is very important. Now, in CAD designing, we normally design to nominal when we make the CAD model. Occasionally, I will design something with the tolerance built into the model, but usually all of that is handled in the drawing. So the solid model's at nominal, and then you tolerance in the drawing. Let's jump over to our drawing. Normally, we'd make separate drawings for both these parts, but it's real handy to be able to see both of them as we talk about this. So over here, I've got the core pin and the stripper sleeve here. So let's work on the core pin first. On this first view here, I'm going to call out the angle of this tapered shutoff. Now, the angle is actually really critical. If this angle drifts out too much, it's going to either shut off too close and put all the pressure up on one point, or too far back. And if it shuts off too far back, we're going to have a gap up here between the sleeve and the pin for plastic to flow down. So tolerancing this correctly is important. And you may think, man, 1/4 of a millimeter, that's a tight tolerance. I actually would probably reduce this even a little bit more. I would be worried in this situation that we're leaving a little bit too much space to cause some less than ideal shutoff situations here. But that angle is really a key controlling dimension of this taper. And then our other key controlling dimension is at the front here. Now, calling this out at the front, we could call this anywhere out along the taper, but we would have to add in another dimension. We'd have to say, okay, this is, 1/4 of an inch back from this shutoff surface. That's where we're going to measure, and it should be this dimension. And that gets kind of tricky to do when you're measuring, when your QA is measuring to check, when the machinist is measuring to see if he's made it right. That's a tricky spot to measure. So we really either have up here at this junction or here. One of those vertices is where we're going to measure this at. And to make these cost effective, we're not going to hold the tolerance on this dimension really tightly. It's really not necessary for this product. We're going to buy an off-the-shelf pin and then have it manufactured, cut down to the shape we need it to be. So this, we're going to live with whatever tolerance that is off the shelf. So our real controlled area is going to be this point right here. So you can see that's where we're going to call out our dimension. But there's a catch here. This is also the area we're going to vent, right? So we're going to do a call out before venting and then a note to add a vent afterwards. So let's talk about this call out. We have the nominal dimension of 0.2561. And then we have this kind of funny looking tolerance, a minus 0.002 and a minus 0.006, or 0.2 of a thousandth and 0.6 of a thousandth. Some people don't really like this way of dimensioning, and I'll explain why I do. But some people would rather have this nominal be the midpoint between these two numbers and have a plus or minus tolerance. I like the negative because as a machinist, when I see this print, I know that the design intent for this dimension is to be smaller than nominal. I know that that's critical. I have two negative tolerances here. So if I'm aiming for one end or the other, I know I'm aiming for the small end. I'm going to keep it in tolerance, but I know I'd rather be -5 or minus even 7 than I would be minus 1/10. I know that positive is the wrong way to go on this component. And that's because this is the inner component. This is going inside the sleeve. And so it cannot be too big or it will not fit. If it's smaller, it will still fit, and we can deal with some of those consequences. But bigger, it's going to be a problem. So I have the negative tolerance. You also see that this is a tight tolerance. This is going to be an expensive part of this to machine. It's going to mean we're going to put this in a highly accurate grinder, and it's going to mean that it has to be held. The vendor is going to charge us more money for this tolerance. That's important to know. We're putting this tolerance because it's necessary and we know it's adding cost. But when we look at some of our other tolerances, we can see that we don't need them so tight for the function. So take this 50 thousandth vent land here. This is a 2 decimal place. You can see I don't have any extra callouts next to it for tolerance. That means it goes off our title block tolerance. So if we go down here to a title block, we see that a 2-place dimension, excuse me, a 2-place decimal is a plus or minus 5 thousandths tolerance. So on our 50 thousandths dimension here, we have a plus or minus 5 thousandths, which is going to work great because length on this is not very critical. If it's 5 thousandths short, 5 thousandths long, it's still going to do its job. Same thing on our radius call out here for our vent dump, not critical. However, our depth is a little bit more critical. We're calling this out, if we go back to our title block on our 3-place dimension, that's plus or minus 1 thousandth. That's because if we did plus or minus 5, we risk this being much too shallow. Excuse me. But plus or minus 1 thousandth is going to put us in a great spot. So we use tolerancing where we need it. Really tight, medium, tight, and then our very loose tolerances. And I haven't dimensioned the rest of this core pin because it's kind of outside today's discussion, but there's even going to be some other tolerances here that can be loose because they're not so critical. They're not controlling dimensions. Let's go over here and we can look at our stripper sleeve. You'll see we're calling out the same dimension there, our same nominal, but on this one we have a plus plus tolerance. Same reason as I like on the core pin to do the minus minus. This is communicating the stripper sleeve is the big side. It's going to be better if we stay on the bigger side of the tolerance. We're going to be safer on the high side. So we have the plus 2/10, plus 6/10. This also, in SolidWorks at least on our drawings, this keeps us from having to play around and adjust this nominal dimension. This is straight from the CAD. It doesn't change. Makes it really simple to do our drawing. Versus if we wanted to force this to nominal, we'd have to play around and tell SolidWorks we want this to be a different dimension than what's shown in the solid model. All right, same thing over here. We've got our 20-degree call out on our angle with our plus or minus 1/4 of a degree. So these tolerances aren't just pulled out of thin air. We have to evaluate the tolerances and make sure that they are going to work with our stack up. There's some things that we're not showing here, critical dimensions of the plastic part, the rest of the tolerancing of this mold that are going to partially play into this. But a big part is it's going to be making sure that our high and our low don't overlap each other. To illustrate this, I made this Excel spreadsheet here. This is pretty simple, but whenever I'm working on shutoffs, I like to create a little spreadsheet to help me to calculate exactly where I'm going to be on my highs and lows and avoid making a tolerancing mistake that results in parts not fitting together. So over here, we've got our nominal dimension, 0.2561. And then I've got a spot here for our core pin on our sleeve. So we're going to enter in our tolerances. I actually had 6/10 on these two. So we've got our minus minus on our core pin and our plus plus on our sleeve. And then our formulas here are going to tell us what's the biggest this core pin is going to be, and what's the smallest it's going to be, and what's the biggest our sleeve is going to be, and what's the smallest our sleeve is going to be. And then over here, we subtract these from each other. So we take our largest core pin and our smallest sleeve, and we say how much is left in between those. If those are both at their high and low tolerances, we still have 4/10 of a thousandth clearance, which is good. We're not going to run into each other. They're going to fit. Same thing on our sleeve, right? We're going to take our low and high tolerances and find out with our largest sleeve and our smallest core pin, how much space will there be? 1,000th or 12/10 of a thousandth. So we know that that's also going to be just fine. We have over here, remember our rule of thumb, polypropylene doesn't flash until 1.5 thousandths. We're under the flash point, right? Now, this is neglecting some other circumstances. We don't have the part print in front of us, the plastic part print that's going to tell us how critical those dimensions are. We haven't designed the rest of the mold yet, the plates and the holders that are going to keep everything in place and aligned. Those tolerances need to be factored in too, and could result in us changing some of this. But as a general rule, we know that we're not going to bind up. We're in a good spot. One last thing I wanted to mention, because it's very applicable, is choice of materials. When we have these two surfaces rubbing against each other, we've already made it ideal by making a tapered shutoff, but there's also some other things to keep in mind. Steel type and hardness. If we have two steels of the same type and the same hardness, we are going to induce galling. That is a principle of metallurgy. When you have not dissimilar enough steel types and not dissimilar enough hardnesses, it will be prone to galling. So as we look at these two parts, we're going to choose dissimilar steels, and we're going to try and make sure that we have at least a few points Rockwell hardness difference between them so that they're not prone to galling up. Galling is where you start to wear and the metal particles start to kind of stick to each other. You look at it, it looks like a mix between scratching and almost little weld splatter building up, and it creates a rough surface on these sealing surfaces. We don't want that. So we're going to be mindful of our steel selection and steel hardness when we spec these to be manufactured. So that's a quick primer on tapered shutoffs. If you have questions, if you have something to contribute, if I'm saying it wrong, completely different than the way you do it or you've heard about doing it, let me know in the comments. We'd love to have discussions on this stuff, and there's just not enough mold making knowledge available in the world. So please drop a note in the comments, ask your questions. We'll try and respond to them. Thanks for tuning in.